Hello, welcome to CSC 7013, Advanced Math for Computer Scientists. This is the second part of Module 8, the Finite Automata 2. In Module 8.8, we discussed the non-deterministical finite automata, the MFA. Also, we provided some examples of NFA. Now, in the second part of Module 8, the 8b, we're going to discuss the difference between the deterministic finite automata and the non-deterministic finite automata. And then we're going to talk about all these various different operations on languages. Remember, language is a subset of sigma star. So if you cannot remember this, just go back to the previous module and review it. And then we're going to talk about regular languages and also the regular expressions. We mentioned earlier that the difference between DFA and NFA is the transition function. Okay, now in DFA, for every state and input, the machine, the finite automata machine, gonna move to a next state, and this next state is uniquely defined by the transition function. In the NFA, that's not the case. If the current state is A or B, then the transition function can move the state from the current state to any other state, or it can even move to nowhere. Also, the current state can just actually move without any input. So we just mentioned that the current state A, can combine with the epsilon, then you can probably still move to A or B or A and B. So that's the reason why it's called a non-deterministical finite automata. Okay, now A could combine with the input 0 or the input 1, and then you're going to move to, also move to various different destinations. So that's the major difference between the DFA and NFA. Now, it's not hard to show that every language accepted by DFA can be accepted by some NFA. Now, that's because NFA is actually a kind of relaxed form of the definition of DFA. So in another word, it means that every DFA is itself also an NFA. Okay, so NFA could be more relaxed, but DFA is very strict. But it's a warm. It also can be regarded as an NFA. So DFA is a special form of NFA. So we're going to illustrate these differences with two examples next. Okay, let's look at the example. We want to build both DFA and NFA to accept binary strings that ends with 0, 1. That means we want to build a finite automata, whether it's a DFA or NFA. We want to accept the strings that ends with 0, 1. So that means the string the finite automata can accept are either 0, 1, 0, 0, 1, because that ends with 0, 1, or 1, 0, 1, 0, 0, 0, 1. or 1 0 0 1, and etc. Okay, so let's start with DFA. So we want to build a deterministic finite automata to accept the binary strings that end with 0 1. So for the deterministic finite automata, we know that we have to make sure that for the transition function, if the current state is A, so then we need to actually define the unique next state for every import value. So that means, so with the current state, we have to actually define the function, defines the next state for every import value. Okay, let's check that one. So let's start with A. Okay, now if the next import is 0, now this is a good import because if the next import is 0, that means we are actually one step closer to the accepting state, right? So let's say we go to state B. Now, if we are in state B, that means the previous import value is 0. So if we got import 1 at the state B, and then we end up with the accepting state, right? Now, remember, we have to build the next state for every import value, okay, for each state. So let's actually look at each of the state. Now, if we are at the state C, so that's accepting state. But if our next import value is, say, 0 or 1, so if whatever the string is, we end up with 0, 1. But if we have a next import value 0 or 1, so then either way, the new string is no longer an accepting string, right? Because it does not end with 0, 1. The first one ends up with 1 0. The second one ends up with 1 1, right? So that means we have to actually, the next state is not accepting state anymore. But where are we supposed to go? Now we need to decide what's the next import. If it's 0, then where we're going to go? Now, if it's 0, that means there's a chance that if we get next import 1, then we're back to the accepting state, right? So that means if the current state is C, the next import is 0, we're not going to go back all the way to A, we go back to B. Because B basically means the previous import is 0. So that means if the next import is 1, then we're back to the accepting state. Okay. Now, if our current state is C, the next import is 1. So that means that's more complicated because that means that in order to make the string an accepting string, then we have to actually, have an import value 0 and a 1 again. So that means in this case, we have to move the state all the way back to A. So we have to build from the very beginning, build a string from very beginning to be an accepting string. Okay, so that's for C, right? Now, if the current state is C, we actually define the next state for each import value. For import value 0, we're back to B. Import value 1, we're back to A. Now for A, let's look at the A. We already defined the next state if the import is 0. Now what about the import is 1? Now for import 1, we should stay at A, in the state A, right? Because we have to make sure the next two state imports value 0, 1 to reach the accepting state. But if its import is 1, then we stays in A, so we're waiting for the next import. If the next import is 0, then we go back to B, and if the next import is 1, we go back to C, right? So we just actually define all the state for the actually current state A. Okay. Now let's see what's the actually state B. For state B, we have defined the next state, which is C, for import 1. But what about the current state is B, but the import value is 0? Yes, that's correct. We stays in B. Because if the next import is 1, then we're back to the accepting state. So basically, we define all the actually states for all the import value. Okay. We look at A, B, C. So for each state, we define the next state for all import values. That's the deterministic finite automata that accepts the binary strings that ends with 0, 1. Okay, let's work on the NFA. So build an NFA to accept the binary strings that ends with 0, 1. Okay. So the NFA will be easier to build because with some imports, the machine can move to multiple states or doesn't have to move to a state at all. So it's relatively easy to build. Okay, now let's start with state A. And it doesn't matter what's the current import. It could be either 0 or 1, right? Now once we got the next 0, we're going to move to a next state B. Okay, in order to make sure the string actually ends with 0, 1, then if we are in B, that the next import should be 1, then we are going to the accepting state. And we should not mention any imports at all after the accepting state C, because we want to build the NFA to accept a binary string that ends with 0, 1. And now that's 0 and 1. We hope that it ends with 0, 1. Okay, if it does not end with 0, 1, then we can reject the string. If there's a whole bunch of imports before the 0, 1, then you can actually include this in the A. Okay. Okay, let's take a look at another example. Build both DFA and NFA to accept the binary strings that starts with 0. Okay, let's first look at DFA. So we want to build a DFA to accept a binary string that starts with 0. So every string like 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, these are all the string that the machine can accept, right? Because it all starts with 0. Okay. Now for DFA, let's start with A. Okay. Now, if the import value is 0, that means this is a string that we're going to accept, right? Because we have actually start with the import 0. Okay. Now, if the import value is 1, then we're going to go to another state, which is C. Okay. Now, it doesn't matter what's the import value if we reach the C, because that string always starts with 1. Okay, it doesn't matter what's the follow-up import values. So this is going to stay in C. That's a trap state, right? Now, if it's actually start with 0, now we end with accepting state B, and then it doesn't matter what's the follow-up import value, 0 or 1, either 0 or 1. It's going to be an accepting state. Stay in the accepting state, right? So it's pretty simple for the DFA in this case. Now let's build the NFA to accept the binary strings that start with 0. Again, NFA going to be simpler, right? So let's start with A, state A. Now, if the import value is 0, then we actually go to the next state, B. Now, since this NFA going to accept binary strings that start with 0, then we actually enter the accepting state, right? And then after this, it doesn't really matter what's the next import. It stays in the accepting state, right? Because it always starts with 0. Now, for any other state, if we currently start with A, for any other import, it doesn't matter. We don't care. As far as once its import is 0, the first import is 0, then we go to the accepting state. So it's that simple, right? That's the NFA. Okay, let's summarize the differences between DFA and NFA. So for DFA, the next possible state is distinctly set. So with the current state, the next state is uniquely determined by the import value. Now in NFA, each pair of state and import symbols can have many possible next state. And backtracking is allowed in DFA. So that means if the current state is A, then with certain import, then the next state is B. And then if the next state is B, in the state B, then if for certain import, we can go back to the previous state. Okay, in NFA, backtracking may or may not be allowed. Okay, now I'm going to skip the next one. So let's say the empty string transition. DFA cannot use empty string transition. Okay, the NFA can use the empty string transition. So that means that you can actually, move to the next state without any import value. Okay, import string. Now state transition, for every symbol of the alphabet, that's for DFA, for every symbol of alphabet, there's only one state transition in DFA. Okay, so if the current state is A, okay, then for every symbol of the alphabet, 0 or 1 or A or B, and there's only one state transition. You're going to move to B. Or for different alphabet, you're going to move to different state. Okay. Now, for NFA, no user specifications are required for making NFAs react in line of symbol. Okay. So that means the transition can occur without import value. Okay. Now, string rejection. DFA rejects strings that in each case the termination state is other than the accepting state. Okay. So because the transition is actually it's well defined. So with the current state, for each import value, the next state is uniquely defined. So if the string actually using the state machine, using the deterministic finite automata, the last actual state is not accepting state, then we reject it. Now NFA is kind of different. NFA rejects the strings only when all branches of NFA are dead or that do not accept the string. So because remember, if we are in the current string with a value, import value, it may actually end up with different string, right? And then for each current state may end up with different string. Okay, so you may have multiple destinations. So as far as one of the final state is accepting state, then the NFA going to accept the string. So for example, you have a multiple destination, and this is actually accepting state, then we accepted the string. Okay, if none of the strings are all the final state are not in accepting state, then we rejected the string. Now transition from one state to another. In DFA, we cannot move from one state to another without consuming the symbol. That means the import. Okay. Now for NFA, this transition may occur without import value. Okay, so that means the import is epsilon. Okay, that's the major differences. Okay, so before we talk about operations on languages, let's first recall the terminology which we just defined in the previous module, the module 7. Okay, now we know that the sigma is the set of alphabets. So sigma could be 0 and 1, right? Or sigma could be A, B, C, D. Okay, it's a set of alphabets. And then we define the sigma star as all the combinations of the alphabet. It's a string just formed by the combination of the alphabet, and also including the empty string, which is epsilon. So if we talk about sigma as a 0, the set of 0, 1, then sigma star going to be epsilon 0, 1, 0, 0, 0, 1, and 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, and all the combinations. Okay. So that's a sigma star. It's a set of all possible strings over the alphabet, sigma. Okay. Now, then we define the language. Language is just a subset of sigma star. Okay. Language could be finite language or infinite language. So that means the language contains an infinite number of strings. Now, let's back to the current topic, operations on languages. Okay, so we know what's a language, right? It's a subset of a sigma star. Okay, now let's A, which is a subset of sigma star, and B, another subset of sigma star, be two languages. Okay, now we're going to define 3 operations on these languages, A and B. So first we define the union. It's the same definition as in the set theory, right? We have 2 sets and then union of 2 sets. So now we treat language as a set. Okay, so A union B, which is defined as all the elements or the string that either this string belongs to the first language A or the string belongs to the second language A. Okay, that's the union of two languages. Now concatenation A circle B, it's a small circle, is defined as the concatenation of the string X and Y. Well, X is from the language A and Y is from language B. I'm sorry, here's a typo. So that's the concatenation of two languages A and B. And then we also, for a language A, we define the cleaning star A star. Okay, and this is defined as x1, x2, x3, and all the way to xk for any integer k. K could be 0, 1, 2, and any integers. And each xi is a string in the language A. So xi could be x0 or x1, x2, all the way to xk. So each x1 is the string in the language A, x2 is a string of the language A. Okay, so we define these three operations for the language. Okay, now here are some examples. Suppose A is a language which contains A and a PQ. B is a language which contains three strings, XY and a UV. Now, the union of A and B is defined as, the union of two languages, right? It's just like a union of two sets. Okay, it contains the element which is either from the language A or the language B. Now the concatenation of A and B is, the first coming from A, the second one coming from B. So if it's, the A is actually, A contains two strings, so that means it could be A and then combined with B, AX, and then A, Y, A, U, V, right? So then let's talk about B, BX, BY, BUV. So there are a total of 6 elements in the concatenation of A and B. Now, cleaning star of A is defined as, the combination of, it's all the concatenation of the, strings in the language A. Because K, look at the definition, K also includes 0. So that means it could be actually contains no string. So it could include the empty string. Okay, so it says epsilon and then A, that's from language A. Remember, A is A and PQ, right? So then PQ, okay, and the A PQ, because that's A is the first one, PQ is the second one, and the AA and PQ PQ, right? Because PQ is the string in this language A. So the cleaning star is actually defined as the combination of these, concatenations of all these, strings in A. So it looks like it's an infinite, infinite set, right? A star is an infinite set. That's a clean, clean star. So let's define the regular language. What is a regular language? Now, the set of regular languages over the alphabet sigma is defined recursively as below. Okay, now first let's define two symbols. The phi, which denotes the empty set, and the epsilon, which denotes the empty string. Okay. Now you will see the difference between these two. One is a set, the other one's a string. So the empty set, empty string. Now let's define the regular language as this. So the set of regular languages over the alphabet sigma is defined as these. We use the three actually rules. The first rule is called basic clause. Okay. In basic clause, we say that the phi, which is the empty set, the set contains no element, is a language, a regular language. Okay. Now, then we define a set which contains the empty string. Okay. We use L of epsilon. Okay, which is the empty string. So which is the curly bracket, and there's an epsilon inside. Now you should know the difference between the empty set and the set which contains the empty string. Okay. Now empty set contains no element in the set. Now empty, the set contains the empty string is not an empty set. There's one element in the set. That's the epsilon. Okay, so that's different. This one contains an element. So first, the empty set and the set contains the empty string. These two are regular languages. Okay, and then if for any x in the epsilon, so if x is any alphabet defined in the epsilon, then the set that contains x is a regular language. Okay, so phi, L of epsilon, and L of x are regular languages. That's rule number one. Now the second one is the inductive clause. Now what does inductive clause mean? That if L of R and L of S are regular languages, so that means the set built from R and the set built from S, if these are regular languages, then the union of LR and LS is a regular language. The concatenation of LR and LS is a regular language. And a clean star of LR is a regular language. So these, after the operation union and the concatenation and the clean star, it's also a regular. These are also regular languages. Okay. Now the last rule, rule number 3, is called the extremal clause. So nothing is a regular language unless it's obtained from the above two clauses. So everything built from the basic clause and the inductive clause are the regular language, and nothing else. That's the regular language. Now that's a definition, the recursive definition. So let's actually build a regular language from the scratch. Okay. And then we can define any language belonging to the set of regular languages over an alphabet sigma is a regular language. Okay, so that means every actually subset of the sigma star is a regular language in this sense. Okay, now we know how to construct a regular language using the definition of regular language. It's a recursive definition. Now here we use another term which is called a regular expression. Regular expressions are used to denote the regular language. Okay. So it can represent the languages, the regular languages, and operations on them succinctly. Okay. So the set of regular expressions over an alphabet sigma is defined recursively as below. Okay. So any element of that set is a regular expression. Okay. So here's the definition. It's very similar to the definition of regular language. Okay. We have basic clause, which basically means the empty set, empty string, and X are regular expressions. Now we don't use the set anymore. We use the expressions. Phi, epsilon, X are regular expressions corresponding to the language Phi, and the set of empty string and the set of X respectively. Here X is in the sigma, which is an alphabet in the sigma. Now with this Phi, epsilon, and X, we can build the regular expressions inductively using inductive clause. So if X and S are regular expressions corresponding to language L of R, or R and S, not X and S, LR and L of S, then R plus S, that's basically the union, RS, that's concatenation, and R star, that's clean star, are regular expression corresponding to the language L of R union L of S, L of R concatenate with L of S, and LR star, respectively. And the last one is the extremo clause, which says nothing is a regular expression unless it's obtained from the above two clause. So that's the definition of regular expression, which is very, very similar, or in parallel to the regular languages. Now, here are the conventions on regular expression. So we know in regular expression we use the three operations: star, which is a clean star, and the plus, which is in parallel with the union, and then we use the concatenation. So based on the convention, the operation asterisk or star has precedence over concatenation. Okay, which has a precedence over union. So basically, I'm taking it wrong. So this is the actually highest one, and next one is concatenation, and then the union. Okay, so that's the precedence. Okay, that's the highest. That's lower. Okay, so that means if we have any regular expression like A plus B circle C star, so based on the conventions, this means we're going to actually evaluate C star first. Okay, and then we're going to evaluate the concatenation, and then last we evaluate the plus. Okay, so if we're going to use the concatenation repeatedly, so the concatenation of k r's, so we have for example 3 r's or 4 r's, then where r is a regular expression, then the concatenation of 4 r's is going to be written like r to the fourth. So if we have a krs, you have krs, then it's going to be written as r to the k. Okay, and also the language corresponding to rk is lk, lr of k. That's the corresponding language. That's the regular expression. Well, L of R is the language corresponding to the regular expression R. So that's basically the convention for these three operations. Okay, again, let's take a look at some of the examples. Now, suppose we have a regular expression, 0 plus 1 to the 2. Now, we know that to figure out what's the corresponding language, then we know that 0 plus 1 is the regular expression corresponding to the language L of 0 union L of 1, that's 0 union 1, or it's 0 and a 1, right? So now 1 plus 2 square basically is the concatenation of these two regular languages. So this is actually corresponding to you pick a 1 in the first language, 1 in the second language, 1 in the first language, and the second language, 1 in the first language, and 1 in the second language. 1, 1, 1, 1. So that's 1, 1. So this is actually the regular expression corresponding to the regular language 0, 0, 0, 1, 1, 0, 1, 1. Okay, so that's the set of strings of length 2 over the alphabet 0 and 1. Okay, now let's look at the second example. Let's first actually erase the first one because we're running out of space. Let's look at the second example. Okay, so 0 plus 1 to the r, or to the k. Okay. So 0 plus 1 to the k. So again, 0 plus 1 is corresponding to the language 0, 1, right? So to the k, that means it's a concatenation of k regular language, the same regular language. So basically, you're gonna actually create the element by picking 1 in the first language and then 1 in the second language and 1 in the third. So you have a total of k zeros. And then pick a 1 in the first language, regular language, pick a 1 in the second language, pick another 1 in the other language, last one I pick a 2. So that's total of k minus 1, 0 and a 1, 1. And so it's 1, 0, 1, 0. Total of length k. So this is actually 1 plus 0 plus 1 to the k corresponds to the set of string of length k over the alphabet 0 and 1. Okay. Now what about 1 plus 0 plus 1 star? So that basically corresponding to the set of string over the alphabet 0 and 1. So it's all the combination of 0 and 1. Okay. Also including the empty string. So 0, 1 star, the clean star actually corresponding to epsilon 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, and and 0, 0, 0, da, da, da. So this is how we actually going to use the regular expression to represent irregular languages. Okay, now let's look at another example. 0 star, 1 star. Now, before we understand what does that expression, regular expression, means, we first need to figure out, how we can interpret this regular expression. So we need to figure out the convention of the regular expression. We remember that the operation star always ahead of concatenation, ahead of union, right? So in this case, we can interpret this as 0 star and the concatenation 1 star. So we always figure out what is the clean star of 0, what's the clean star of 1. So this first one is epsilon 0, 1, 0, 0, 0, 0, 0. That's a clean star of 0. And the concatenation epsilon 1, 1, 1, 1, 1, 1. So now that's a concatenation. So you need to pick one element from the first language, another element from the second language, and you can actually include all this combination. So this is going to give you epsilon 0, 0, 1, 0, 0, 0, 1, 1, and let's see, 1, 1, right? Because if the first one is epsilon, the second one is 1, 1, that's 1, 1, because that's empty string. Okay, let's actually cross this one out. Always actually start with the string with a short length. Now what about 1, 0? Now 1, 0 is not in this language, because in this language we have a concatenation of 0 star and 1 star, so the 0 is always ahead of 1. So 1, 0 is not. Okay. So now you have a 1, 0, 0, 1. That's okay. 0, 0, 0, 1, 1. That's okay, right? 1, 1, 1. That's okay. Can we have like 0, 1, 0? No, because that 0 is actually after 1. This is not going to happen. Okay. So we can always build this, oh, we miss 3 zeros, because that's, yeah, 0, 0, 0, 1, 0, 0, 1, 1. Okay. Make sure that they use the combination of, you pick the element from the first, 0 star, and pick the element from 1 star, and then you just use the combination for all. So, for all every string in this language should have 0 at the beginning and 1 later. Or you have no 0 but then all 1s. That's okay. Or you have all 0s without a 1. But if you have a combination of a 0 and a 1, always have a 0 ahead of 1. Okay. Look at the top one, the regular expression of the top one. A plus B, parenthesis, star, A, B, B. Okay. So we always going to, evaluate the expression inside the parenthesis, and then the star, and then the concatenation, right? So so A plus B, it's the regular expression of the language LA union LB, right? That's A union B, and the A, B, which contains. So then we have a clean star of this A and B. So A, B, a clean star. So that means it contains the epsilon, the empty string, A, B, okay, A, B, B, A, B, B. So it's pretty much the, A, B star. So that's the clean. It's all the combination of A and B. Okay. And then the next one could be A, right? Okay. And then that's the concatenation here. So we have the language like if this AB star concatenated with ABB. So this is going to give you, if ABB concatenated with empty string, then give you ABB. Concatenate with A, so we're going to A, B, B. And concatenate with B, ABB. Always end with ABB, okay? Okay, so then A, B, B, A, B, yeah, A, B, B, or with AB concatenate with ABB. So that's the regular languages, associated with the regular expression. Okay, so last one, I'm going to leave that for you. Okay, so how can you interpret this regular expression? So I think that's pretty much all we're going to talk about for the module 8. So that's module B. Okay. Thank you and goodbye.